Today we're going to talk about how the chain rule applies to multivariate functions. So first, I have written out on the screen what the chain rule is for a function of two variables. So if z is a function of x and y, and x and y are both functions of t, then dz dt is our partial z with respect to x times dx dt plus dz dy times dy dt. So one way of thinking about this chain rule is you can kind of draw a tree diagram to describe what's happening with our functions. So z is a function of both x and x and y are both functions of t. And then we have to have a term for each branch of this tree. So we have to take dz dx times dx dt. And then we need a separate term for the other branch, dz dy times dy dt. All right, I'm not going to take the time to prove this for you. Your textbook does that. Let's instead take a look at an example. Let's use the chain rule to find dz dt for z equals x squared y, where x is 2t and y is t squared. So I have my chain rule written out to the right in blue. So I'm going to have to find my partial with respect to x, my partial with respect to y, and then I'll multiply each of those by dx dt and dy dt. Okay, so here's my function, z equals x squared y. So take the derivative with respect to x, I get 2xy. Derivative with respect to y is just x squared. Dx dt is 2, dy dt is 2t. So putting that into my chain rule, I take dz dx times dx dt plus dz dy times dy dt. And then we can actually do some substitution and get our final answer in terms of t only, because we know that x is 2t and y is t squared. And so I'm just going to go ahead and replace the x's with 2t and the y with t squared. And then I can go through and multiply everything out, combine like terms if possible. And let's see, we end up with 8t to the third plus 8t to the third, or 16t to the third. And that's my derivative of z with respect to t. Now I use the chain rule to solve this problem, but to verify that the chain rule is working, there's actually another way we can do this problem. We could just do the substitution first, and hopefully we get the same answer. So what I mean by that, if our function is x squared y, before we take the derivative, we could replace the x with 2t and replace the y with t squared. Plugging that into my function, let's see, I get 2t squared times t squared. That simplifies down to 4t to the fourth. And when I take the derivative, I get 16t to the third, which is the same thing I got when I used the chain rule. So it's nice to see that the chain rule does give us the correct answer. Now in this case, I think the second method is a lot faster. So why are we talking about the chain rule? Well, it helps us solve certain applications, and we'll see some ways that we can use it to solve a couple of different types of problems. So let's start with an application. This problem says the pressure, volume, and temperature of an ideal gas are related by the equation PV equals 8.31 T. Okay, so that's the equation we have. Find the rate at which the pressure is changing when the temperature is 300 kelvins and increasing at a rate of 0.1 Kelvin per second, and the volume is 100 liters and increasing at a rate of 0.2 liters per second. So what this problem is asking us to find is the rate at which the pressure is changing. So how is pressure changing with time? That would be dP dt. We're interested in this when temperature is 300 and when temperature is increasing or changing, so dt dt at a rate of 0.1. And let's see, volume, so V is 100, and volume is increasing at a rate of 0.2, so dV dt is 0.2. So I've basically taken all of the information in this problem and just written it out in symbolic form. Again, our goal is to find dP dt. How is pressure changing? So we can actually use the chain rule to solve this problem. We have this equation, PV equals 8.1T. We can go ahead and solve that equation for P. So P is 8.31T divided by V. And then we can just apply the chain rule directly to this multivariate function. So in this case, pressure is a function of temperature and volume, and each of those are functions of time. So dP dt is going to be dP dV times dV dt plus dP dt times dt dt. So I basically need a term for each of those kind of branches in my tree diagram. And so I can actually go through and figure out what each of these things are, each of these quantities are, and then just plug the numbers in. Okay, so looking at my equation, here's my function, pressure function. I just circled it in blue. P equals 8.1T divided by V. So if I want to find dP dV, I'm finding the partial derivative of P with respect to V. And so my partial derivative is negative 8.31T over V squared. How I got that is I thought of this as 8.31T times V to the negative 1. Brought the negative 1 down and then ended up getting a V to the negative 2. That's why I have the V squared on the bottom there. Okay, so that's my dP dV. And then I have to take the derivative with respect to temperature, T. So I'm going to find dP dt, my partial derivative with respect to temperature. And the T is on the top, it's just a linear term. So that derivative is going to be 8.31 divided by V. So I plugged those things into my chain rule. And then finally, I have a bunch of numbers I can plug in. We know temperature is 300, so I can just replace the T with 300. Let's see, volume is 100, so I'll put that in for the V's. And then they did also give us the dV dt. So where is that? dV dt was 0.2, and how temperature is changing with time is the 0.1. And so I can just go ahead and plug all of those numbers in, use my calculator to finish this, and there's my final answer, negative 0.042 kilopascals per second. So knowing about the chain rule for multivariate functions gives us another way to solve. This is actually a related rates problem, so you might have seen a problem like this in Calc 1. So there is another way to solve this problem, but the chain rule gives us just an alternative way of thinking about this. We can now think about this problem as a multivariate function and apply the chain rule directly to it. Now, we can extend the chain rule to functions of more variables. So for example, in this case right here, I have z, which is a function of both x and y, and then x is a function of u and v, and y is also a function of u and v. So in this particular case, we are capable of finding the partial derivative of z, the output, with respect to u. So my final input variables are u and v, so I can find the derivative of z with respect to u, or I can find the derivative of z with respect to v. And so I have written on the screen how we would do that using the chain rule. So you can kind of draw a tree like this to help you see where these formulas come from. But if we want to find the derivative with respect to u, we're going to have to do dz dx times dx du. And then we'll have to do dz dy times dy du. And that'll give me my partial derivative with respect to u. If we want to find the derivative with respect to v, we would have to do dz dx times dx dv plus dz dy times dy dv. We'd have to do the branches that end with v's, basically. And we can extend this idea to really any number of variables. But let's take a look at an example that uses this idea. So if z is e to the x sine of y, and x is uv squared, y is u squared v, let's see if we can find our partial derivative of z with respect to u and with respect to v. So I'm going to start with my dz du, and on the screen I've just copied down what the chain rule would be. I'm going to have to take dz dx times dx du plus dz dy times dy du. So let's go ahead and compute each of those components. So here's my function z, I'll circle it. Take the derivative with respect to x. So derivative of e to the x is e to the x. So I just get e to the x sine of y. Derivative with respect to y is going to be e to the x cosine y. All right, and then if x is uv squared, dx du is just v squared, y is u squared v, so dy du is 2uv, and then we'll go ahead, we'll plug that into our formula. So I took those derivatives, plugged it into my chain rule formula, and then finally we can get our final answer in terms of u's and v's by just going through and replacing the x's and y's with the given expressions. So I just rewrote the first term. I put the v squared in the front, so v squared, and then e to the x turned into that e to the uv squared, and then we get, let's see, sine of u squared v, that's my sine of y, and then for the second term I put the 2uv in front, and then same idea, e to the uv squared cosine u squared v. So there's my derivative with respect to u. And we can go through and do something very similar to find our derivative with respect to v. This time we're going to apply the chain rule to get dz dx times dx dv plus dz dy times dy dv. And so I've already found my partials with respect to x and y in the previous problem, so I won't repeat that part. So I guess the only thing new that I had to do here is find my dx dv. So again, x was uv squared, so I get 2uv. And then if y is u squared v, my derivative with respect to v is just u squared. And so I can take these expressions, these derivatives, plug them into my chain rule. And now I have dz dv equals my e to the x sine of y times 2uv, e to the x cosine y times u squared. And then finally, we can get that final answer in terms of u and v by just going through and substituting the given expressions, the uv squared for x and the u squared v in for y. And so at the bottom of the screen, there's my final answer. That's my derivative with z for z with respect to v. All right, so that's an example of how we can apply this if we have a function of two variables, which are also functions of two variables. But again, this idea can be extended to really any number of variables. Finally, the last thing I wanted to run through in this section is I want to show you that the chain rule for multivariate functions gives us another way of thinking about and solving problems that involve implicit differentiation. So implicit differentiation is something that hopefully you saw in Calc 1, and it's the idea where you have an equation with x's and y's, but it's not solved explicitly for y. And so then you took the derivative one term at a time, and you probably had to put these y primes in there, and then eventually solve for y prime. So again, it was a technique that would allow us to find derivatives if our equation is not solved explicitly for y. And so over to the right on the screen is an example of what an implicit differentiation problem might look like. So what I'm going to show you is how we can use our chain rule to solve these problems in a slightly faster way. So let's start out by saying we have some function z, which is a function of two variables x and y. But we're going to extend to this idea, and we're going to say that the y is actually a function of x, because that's what we're assuming when we do these implicit differentiation problems. Okay, so just applying my chain rule to z to find, say, dz dx. So let's say I want to find dz dx. I would find my partial of z with respect to x, and I guess technically times dx dx. And then I'd find my partial with respect to y times dy dx. Okay, so that is just simply my chain rule applied on the function z equals f of xy. Now, let's say our f of xy equals 0. So, okay, so let's just say that this particular equation is equal to 0. Then when we take the derivative, our dz dx would have to equal 0 because our function is equal to a constant. If you take the derivative of both sides, it's going to have to equal 0. So my dz dx equals 0. And then I just copy down partial of z with respect to x. Dx dx is just equal to 1. That's basically saying if you take the derivative of x with respect to x, so if you just take the derivative of x, you get 1. And then I just copy down my partial z with respect to y, and then dy dx. So that's what I plugged into my equation. And then I get something that I can actually solve for dy dx. So we can minus the dz dx and then divide by dy dx. And so what I'm left with is dy dx is going to equal negative partial of z with respect to x divided by partial of z with respect to y. Or using our other notation, we could say it's going to be negative f sub x divided by f sub y. And so that's always true. This is a kind of a fast way that you could find a derivative implicitly. And let me explain this further by taking a closer look at the example I have written on the right side of the screen. So we have this equation 3x squared y plus y squared equals 0. And so we can say that this is our function. F of xy equals this equation, which happens to equal 0. So then if we take the derivative of both sides, the derivative of 0 is just 0. And then we're going to end up with dz dx times dx dx plus dz dy times dy dx, which is exactly what I had typed up on the screen. We solve it for dy dx, and we end up getting dy dx is negative partial with respect to x divided by partial with respect to y. So in this particular case, here's my function f. Derivative with respect to x is just 3y. Derivative with respect to y is 3x plus 2y. And so this formula is saying that dy dx would have to be negative 3y over 3x plus 2y. And you can verify this if you remember how to do this implicitly from Calc 1. You can actually solve this and verify that this is indeed the answer. So let's do another example. Let's take a closer look, do another example. I did actually write down on the screen how you would do this implicitly, so feel free to pause and take a look at that if you're interested. But in my next example, I just want to focus on this using the chain rule, this new method. So here's the problem I want to solve. Use partial derivatives to find dy dx for x cosine y plus y cosine x equals 1. So I'm going to call this equation my z. I'm also going to set it equal to 0. In this case, it would actually be okay if we left it equal to 1 because 1 is a constant, but I just get in the habit of setting it equal to 0 because if the right-hand side had variables in it, that would matter. So I'm just going to let my multivariate function z equal this equation set equal to 0. So z is x cosine y plus y cosine x minus 1, and that happens to equal 0. So then I'm going to find my partial derivative with respect to x. So that would be cosine y minus y sine x. And then I'll find my partial derivative of z with respect to y. That should be negative x sine y plus cosine x. And that means dy dx would be negative partial with respect to x divided by the partial with respect to y. And so right away I can quickly write down what that derivative is. And so this application of the chain rule is a little bit faster than that implicit differentiation that we learned in the past. All right, that was my last example. Please let me know if anything in this video is unclear.